Hello and welcome to Science for Bedtime. This is a space where science can unfold slowly, without pressure, and where attention is free to come and go. The universe we are about to explore does not demand focus or effort. It simply exists, changing gradually, according to rules that have been shaping it for billions of years. When astronomers observe distant galaxies, they notice a consistent pattern in the light those galaxies emit. The light is shifted toward longer wavelengths, a phenomenon known as redshift. This shift increases with distance, suggesting that galaxies farther away are receding faster. The most widely accepted interpretation is not that galaxies are flying through space, but that space itself is expanding between them. This expansion has been measured through multiple independent methods and forms a cornerstone of modern cosmology. As space stretches, it carries light along with it, elongating its wavelength and reducing its energy. Over immense periods of time, this stretching reshapes the large-scale structure of the universe, increasing distances between regions that are not held together by gravity. Alongside this expansion, the universe carries a faint background signal that offers a glimpse into its early state. The cosmic microwave background is radiation left over from a time when the universe was hot, dense, and filled with plasma. At that stage, light could not travel freely. When the universe cooled enough for atoms to form, this radiation was released and began its long journey through space. As the universe expanded, this radiation cooled. What was once intense, high-energy light has been stretched into microwaves with extremely low energy. The cosmic microwave background is remarkably uniform, with only tiny variations that reflect early density differences. Its steady cooling shows how the energy density of radiation drops as the universe expands. This gradual cooling connects directly to the concept of entropy. In physics, entropy is a measure of how energy is distributed within a system. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This does not mean disorder in a casual sense, but rather that energy spreads out and becomes less available to do work. On the largest scales, the universe is often treated as effectively isolated. Energy that was once concentrated in hot, dense regions gradually disperses as space expands. Temperature differences smooth out. Over time, processes that depend on sharp contrasts in energy become harder to sustain. This trend is well supported by observation, though its ultimate limits remain an active area of research. Stars represent one of the clearest examples of energy concentration in the universe. A star shines because gravity compresses its core, allowing nuclear fusion to convert mass into energy. This process is stable for long periods, but it is not permanent. Each star contains a finite amount of fuel, and the rate at which it is consumed depends strongly on the star's mass. Smaller stars burn their fuel slowly and can persist for trillions of years, while larger stars live much shorter lives. Regardless of size, all stars eventually exhaust the fuel that allows fusion to continue. When that happens, their structure changes, leading to a variety of stellar remnants depending on their original mass. Across the universe as a whole, star formation is declining. Observations indicate that the peak era of star formation occurred billions of years ago. Since then, the supply of cold gas needed to form new stars has been steadily decreasing. As galaxies evolve and expand, this gas becomes harder to gather into dense clouds capable of collapse. As star formation slows, existing stars continue to age and die. Low and medium mass stars shed their outer layers and leave behind dense cores known as white dwarfs. These objects no longer produce energy through fusion. They shine only by releasing stored heat, gradually cooling over extremely long periods of time. More massive stars end their lives more dramatically. When fusion ceases in their cores, gravity causes a rapid collapse that triggers a supernova. What remains can be a neutron star, an object so dense that protons and electrons have merged into neutrons. In cases of even greater mass, the collapse continues, forming a black hole. These remnants represent increasingly stable configurations of matter. White dwarfs and neutron stars resist further collapse through quantum mechanical effects, while black holes represent regions where gravity dominates completely. In the far future, as active stars disappear, these remnants become the primary structures remaining. Black holes are often described as permanent, but current theoretical models suggest they may not last forever. According to quantum field theory applied to curved spacetime, black holes are expected to emit a very faint form of radiation, known as Hawking radiation. This process has not been observed directly and remains a theoretical prediction, but it is widely studied. If Hawking radiation occurs as predicted, black holes would lose mass extremely slowly. For stellar mass black holes, this process would take vastly longer than the current age of the universe. For the largest black holes, the timescales are even more immense. Over enough time, however, these objects could gradually evaporate. The combined effect of expansion, declining star formation, and the slow evolution of remnants leads many cosmological models toward a similar long-term picture. In the standard LCDM model, which includes dark energy as a cosmological constant, the universe continues expanding indefinitely. As expansion proceeds, matter becomes increasingly dilute, and energy differences continue to flatten. In this scenario, sometimes described as a big freeze or heat death, the universe approaches a state where no significant energy gradients remain. This does not imply a sudden end or a dramatic event. Instead, it suggests a gradual transition toward conditions where complex processes become exceedingly rare. Current evidence supports this as a likely outcome, though it depends on assumptions about dark energy and the long-term behavior of physical laws. Other possibilities have been proposed, though they are more speculative. Some models suggest that if dark energy behaves differently over time, expansion could accelerate enough to tear apart bound structures in a scenario known as the Big Rip. Others explore the idea that the vacuum itself could undergo a transition to a lower energy state, fundamentally altering the laws of physics. Cyclic models propose repeated phases of expansion and contraction, though these face significant theoretical challenges. Each of these alternatives remains uncertain and is actively studied rather than confirmed. What they share is an acknowledgement that our understanding of the universe's deepest future is incomplete. Observations guide current models, but extrapolating far beyond observable timescales introduces unavoidable uncertainty. What remains clear is that the universe changes slowly and consistently, guided by principles that do not rush toward conclusions. The far future is not defined by a single moment, but by a gradual thinning of activity as energy spreads and structures fade. In this vast timeline, endings are not sharp boundaries, but gentle transitions that unfold over spans of time far beyond ordinary experience. As the universe continues along this path, distance begins to play a more decisive role than motion or force. Expansion does not merely separate galaxies, it reshapes what parts of the universe can ever influence one another. Light travels at a finite speed, and as space itself stretches, there are regions from which light emitted today will never reach other regions, no matter how long time passes. This leads to the idea of a cosmic horizon. Unlike the event horizon of a black hole, this boundary is not tied to a single object. It emerges from the overall expansion of space. Beyond this horizon, the expansion carries regions away faster than light can bridge the growing distance. These regions are not destroyed or altered, but they become causally disconnected. Over extremely long time scales, this isolation becomes more pronounced. Galaxies outside a local gravitational group gradually slip beyond observational reach. Their light becomes so redshifted and faint that it blends into the background. Eventually, even the cosmic microwave background continues to cool and stretch until it becomes undetectable by any realistic means. Within each isolated region, gravity still acts locally. Stars orbit remnants, particles move. but the larger cosmic web dissolves into separated islands of matter and energy. Each island follows the same physical laws, yet no information can pass between them. The universe remains a single physical system, but no longer connected in the way it once was. As black holes shrink, the energy they release becomes increasingly diffuse. This radiation does not form new structures, it spreads into space that is already expanding, further smoothing any remaining differences in energy density. The universe moves closer to a state where no process dominates over any other. Some uncertainty remains in these projections. Dark energy, while well supported observationally, is not fully understood. Its behavior over trillions of years cannot be tested directly. Small deviations from current assumptions could alter the far future in subtle or dramatic ways. One speculative possibility is that dark energy could increase in strength over time. In this case, expansion would accelerate more aggressively, eventually overcoming not only gravity but other binding forces. This scenario, known as the Big Rip, would unfold gradually at first. Galaxies would separate, then smaller bound systems would become unstable. If such a process occurred, stars, planets, and even atomic structures could eventually be disrupted. This idea remains speculative and is not favored by current data. It is included because it illustrates how sensitive cosmic outcomes can be to the properties of dark energy. Another speculative idea involves vacuum decay. In some quantum field theories, the vacuum state of space may not be the lowest possible energy configuration. If the universe exists in a metastable state, it could, in principle, transition to a lower energy state through a quantum process. Such a transition would alter the fundamental constants and laws of physics within the affected region. This process, if it occurs, would propagate at nearly the speed of light and would not be observable in advance. However, current estimates suggest that if vacuum decay is possible, it is extremely unlikely on timescales comparable to the age of the universe. The idea remains theoretical and unconfirmed. Cyclic models propose a different perspective. In these models, the universe does not have a final end, but undergoes repeated phases of expansion and contraction. Some versions suggest a bounce replaces the traditional Big Bang, while others involve higher dimensional interactions. These models attempt to address questions about initial conditions and entropy, but they face significant theoretical and observational challenges. While these alternatives are intriguing, they are less strongly supported than the gradual cooling and dilution predicted by standard cosmology. Most evidence currently points toward a universe that expands indefinitely, growing colder and more diffuse over time. The pace is slow and the changes are subtle, unfolding over durations that stretch beyond imagination. As the universe approaches this distant future, familiar measures of time lose their practical meaning. Days, years, and even stellar lifetimes no longer apply. Events become separated by intervals so long that comparison becomes difficult. Time continues as a dimension, but it no longer organizes experience in a useful way. This does not mean that time ends or disappears. Rather, it reflects that change has become extremely rare. Without processes to mark duration, the passage of time becomes abstract. Physics still describes evolution, but there is little left to evolve. The universe in this state is not empty in an absolute sense. Quantum fields persist, space retains structure. The fundamental framework remains intact. What has changed is the absence of contrast. Everything that once created difference has settled into uniformity. This uniformity is not sudden. It emerges gradually as the natural outcome of expansion, energy dispersal, and the finite lifetimes of structures. The universe does not collapse into silence. It arrives there slowly, without ceremony, guided only by the steady application of its laws. In this far future, the universe is shaped less by events and more by conditions. What remains is governed by persistence rather than change. Matter, where it still exists, follows trajectories that are stable and predictable. no longer disrupted by energetic interactions or sudden transformations. Within isolated regions, particles continue to move according to local laws. Even in near equilibrium, motion does not vanish. Atoms drift, radiation travels, quantum processes still occur. But these motions rarely lead to new arrangements that matter on large scales. Without dense environments or strong gradients, complexity has little opportunity to arise. One consequence of this thinning universe is that interactions become exceedingly infrequent. Collisions between particles still happen, but the distances involved make them rare. Gravitational encounters between remnants occur only occasionally, separated by spans of time that dwarf earlier cosmic eras. The universe remains active in principle, but quiet in practice. In such conditions, matter itself may face long-term changes. Some theories suggest that protons, which appear stable on all observed timescales, might eventually decay. This possibility arises in certain extensions of particle physics, though it has not been observed experimentally. If proton decay occurs, it would take place over times far longer than the current age of the universe. Should proton decay be real, even the most durable structures would gradually dissolve. Atoms would lose their nuclei. White dwarfs and neutron stars would slowly lose mass as their constituent particles decay into lighter forms. This process would further smooth the universe, converting matter into low-energy radiation and neutrinos. If proton decay does not occur, matter could persist indefinitely in degenerate forms. Even then, change would continue at an extremely slow pace. Quantum tunneling and rare interactions could still alter structures over unimaginable durations. Stability does not imply complete stasis, only the lack of rapid transformation. As matter thins or decays, radiation becomes increasingly dominant. Photons stretch as space expands, losing energy through redshift. Over time, their wavelengths grow so long that they interact weakly with anything else. Radiation fills space, but its presence becomes nearly undetectable. Neutrinos, nearly massless and weakly interacting, also populate the far future universe. Produced in vast numbers during earlier cosmic epochs, they travel almost unhindered through space. Their energy decreases with expansion, and their influence fades into the background. At these stages, distinctions between different forms of energy blur. Everything contributes to a uniform, low-energy environment. The universe approaches a condition where no component stands out as dynamically significant. This leveling reflects the ongoing increase of entropy and the diminishing availability of usable energy. In many descriptions, this era is called the dark era of the universe. Darkness here does not imply absence, but the lack of visible light sources. Without stars or hot objects, the universe emits almost no radiation in familiar wavelengths. What light remains lies far outside the range of human perception. This darkness does not arrive suddenly. It unfolds gradually as the last stars fade and remnants cool. The sky, once filled with structure and contrast, becomes increasingly uniform. Eventually, there are no reference points to define direction or scale. Every location appears much like any other. The absence of structure also affects how the universe could be observed, in principle. With no luminous objects and no background radiation of practical intensity, observation itself becomes meaningless. There is nothing to detect and no vantage point that differs from another. In this sense, the universe becomes extremely difficult to observe, even though it continues to exist. Physics still describes its state, but no process remains that could register that description. This is not a limitation of theory, but a reflection of the conditions themselves. Despite this, the mathematical framework underlying the universe remains intact. Space continues to expand according to the influence of dark energy. Quantum fields retain their ground states. The equations that once described stars and galaxies still apply, even though their subjects have vanished. This leads to a subtle distinction between existence and activity. The universe exists as a stable configuration of fields and geometry, but it no longer expresses that existence through dynamic events. The difference between one moment and the next becomes increasingly abstract. In everyday experience, time is marked by change. A clock ticks, a process unfolds. In the far future universe, such markers are absent. Time continues as a coordinate in physical law, but it no longer corresponds to observable progression. Duration loses its practical meaning, even though it remains well-defined mathematically. This perspective does not imply that time stops. Instead, it reflects that without events, time cannot be operationally distinguished. The universe does not run out of time. It runs out of processes that produce meaningful change. This horizon carries thermodynamic properties of its own. In certain formulations, it is associated with a temperature and entropy, though both are extremely small. These properties suggest that even empty, expanding space has limits on how much information it can contain. If these descriptions are accurate, the far future universe has a finite informational capacity within any given region. Once that capacity is reached, no new information can be stored or processed. This introduces another sense in which change becomes constrained. Quantum fluctuations may still occur, but they are random and short-lived. Without mechanisms to amplify them into lasting structures, they leave no enduring trace. The universe becomes dominated by statistical noise rather than organized behavior. At this point, the difference between physical possibility and physical relevance becomes important. Many processes remain theoretically allowed, but the conditions required for them are no longer present. The universe permits change, but does not support it. This outcome does not represent a failure of the universe or its laws. It is simply the result of their consistent application over immense time. The same principles that allowed complexity to arise also allow it to fade. The far future, then, is not an ending imposed from outside. It is the natural conclusion of a trajectory set by expansion, energy dispersal, and finite resources. The universe does not collapse or disappear. It settles into a stable, minimal form. This stability is not fragile. Small disturbances cannot propagate or grow. Large-scale structure cannot re-emerge spontaneously. The universe remains in a state where nothing pushes it away from equilibrium. And yet, within this stillness, uncertainty remains at the deepest levels. Our understanding of quantum gravity is incomplete. The behavior of space-time at the smallest scales remains unknown. It is possible that new physics operates beyond the regimes we can currently describe. Such possibilities are speculative and should be treated cautiously. They remind us that predictions about the far future rely on extending known laws far beyond tested conditions. Confidence decreases as timescales increase. Even so, the broad outline remains consistent across many models. Expansion continues, energy spreads, structure fades, change becomes rare. The universe grows simpler, not through loss, but through completion. In this way, the far future is less a destination than a gradual settling. There is no final moment when the universe becomes what it will be. It approaches that condition asymptotically, drawing ever closer without crossing a distinct boundary. The universe does not announce this transition. It does not pause. It simply continues quietly, following the same rules that have always guided it, until those rules produce a state where nothing further needs to happen. As the universe settles into this extended equilibrium, questions shift away from what happens and toward what can still be defined. Physical laws continue to exist as descriptions, but the systems they once governed are no longer present in meaningful form. The universe remains mathematically describable, even when it no longer produces phenomena that demand description. One subtle consequence of this state involves information. In physics, information is not abstract. It is tied to physical systems that can store, transmit, or transform it. When stars, planets, and complex matter disappear, the universe loses its primary information-bearing structures. What remains carries very little distinguishable information from one region to another. In an expanding universe dominated by dark energy, information is also limited by horizons. Each region has a finite boundary beyond which signals can never arrive. This means that even if something were to occur elsewhere, it would have no effect locally. Information becomes trapped within shrinking causal domains, isolated and eventually exhausted. Once these limits are reached, no new records can form, no memory can be stored, no process can encode a difference between past and future states. The universe continues to exist, but it no longer remembers itself in any operational sense. History becomes a concept without a physical substrate. This should not be understood as erasure. Past events are not undone. Rather, the physical traces that once carried evidence of those events have dissipated. Without structures to preserve correlations, the universe loses its capacity to distinguish one prior configuration from another. In this context, even probability changes its role. Probabilities in physics describe the likelihood of outcomes given repeated trials or evolving systems. In a universe where no trials repeat and no systems evolve meaningfully, probability loses its practical application. Randomness remains mathematically defined, but it has no observable consequences. Some theoretical discussions explore whether rare fluctuations could still occur in such a universe. Quantum mechanics allows for spontaneous fluctuations even in low-energy states. In principle, a sufficiently large fluctuation could briefly produce structure. However, the likelihood of such events, if they occur at all, is extraordinarily low and deeply uncertain. These ideas are often discussed cautiously because they depend on extrapolating quantum theory far beyond tested regimes. Whether such fluctuations can meaningfully recreate complexity remains unresolved. Most models suggest that even if fluctuations occur, they would be transient and isolated, unable to rebuild a dynamic universe. Another question concerns identity and persistence. In earlier epochs, objects persisted through continuous interaction with their environment. In the far future, persistence becomes trivial. Things persist because nothing acts on them, not because they are maintained. Stability replaces interaction as the defining feature. This also affects how causality functions. Cause and effect still exist locally, but the chains of causation become extremely short. Effects dissipate almost immediately into a background that cannot amplify or transmit them. Large-scale causal narratives no longer form. The universe, in this condition, resembles a system that has completed all possible computations allowed by its energy and structure. Once no further computation is possible, nothing remains to distinguish one state from another. This idea appears in some approaches to cosmology that link physical evolution with information processing. Such interpretations should be treated as conceptual tools rather than established conclusions. They provide a language for thinking about extreme futures, but do not replace empirical science. Still, they highlight an important point. Physical evolution is constrained not only by laws, but by capacity. When capacity is exhausted, evolution halts not because it is forbidden, but because it is unnecessary. The universe has reached a configuration where no further differentiation is possible. It does not resist change, it simply no longer supports it. This state also reframes the idea of observation. Observation requires contrast, a difference between observer and observed. In the far future universe, such distinctions vanish. There is no privileged frame, no reference point, no structure capable of observation. Even hypothetical observers cannot exist without energy gradients and stable matter. Consciousness, measurement, and awareness depend on processes that require ongoing change. Without those processes, observation ceases to be physically meaningful. This absence of observers does not negate the universe's existence, it only removes perspective. The universe does not require witnesses to persist. It exists according to its internal consistency. not according to whether it is perceived. At this stage, cosmology approaches its conceptual limits. Science relies on models tested against observation. When observation becomes impossible even in principle, science can only extend trends forward cautiously. Statements become conditional, framed by assumptions rather than verification. This is why descriptions of the far future are always provisional. They depend on the continued validity of known laws and the absence of unknown processes that could intervene. Confidence decreases not because the models are flawed, but because the distance from testable reality grows. Still, the broad direction remains robust across many independent approaches. Expansion continues, energy spreads, structure dissolves, interaction fades, the universe simplifies. This simplification is not monotonic in every detail, but it is consistent in outcome. There is no known mechanism that naturally reverses it on large scales. Without new physics, the universe does not reassemble itself. What remains, then, is a cosmos defined by uniformity rather than diversity. The dramatic contrasts that once characterized its evolution give way to subtle, nearly invisible differences. These differences, too small to matter, eventually fade. The universe becomes dominated by geometry rather than matter, by expansion rather than interaction. Space itself becomes the primary feature, stretching smoothly without interruption. In this environment, even language struggles. Words like empty, quiet, or still carry meanings shaped by experience. The far future universe is none of these in a familiar sense. It is not empty because fields remain. It is not quiet because silence implies sound. It is not still because expansion continues. It is better described as complete, a system that has expressed every possibility available under its rules, and now remains in the most stable configuration those rules allow. This completeness does not arrive abruptly. It emerges gradually, asymptotically, without a moment of arrival. The universe does not cross into finality. It approaches it endlessly. In that approach, distinctions fade one by one, not because they are removed, but because they no longer make a difference. When differences no longer matter, they effectively disappear. The universe continues, not toward something new, but toward nothing in particular, a continuation without direction, governed by laws that have finished all the work they can do. And in that condition, the universe remains exactly what it has become: consistent, extended, and unchanged, not through stagnation, but through completion. As conditions continue to stabilize, attention turns to the structure of space itself. Space is not a passive container, but a dynamic component of the universe, shaped by energy content and expansion. In current models, the long-term behavior of space is strongly influenced by dark energy, which appears to act uniformly throughout the cosmos. Dark energy is inferred from observations rather than detected directly. Measurements of distant supernovae, galaxy clustering, and the cosmic microwave background all indicate that expansion is accelerating. In the simplest interpretation, dark energy behaves like a constant property of space, often described as a cosmological constant. If this description remains valid indefinitely, expansion continues at an accelerating but steady rate. Under these assumptions, space-time gradually approaches a smooth, de Sitter-like geometry. In such a geometry, large-scale curvature becomes increasingly uniform. Matter and radiation play an ever smaller role in shaping space-time compared to the influence of dark energy. This transition is slow and does not involve abrupt structural changes. One consequence of this geometry is the persistence of cosmological horizons. Each region of space has a boundary beyond which events can never influence it. These horizons are not physical barriers, but limits imposed by expansion. Their existence is well supported within accelerating expansion models, though their detailed properties depend on the exact nature of dark energy. Cosmological horizons also introduce subtle thermodynamic considerations. In certain theoretical treatments, they are associated with a temperature and an entropy. These quantities are extremely small and difficult to interpret physically, but they suggest that even empty, expanding space may have limits on information content. This remains an area of active theoretical work rather than settled understanding. As matter continues to thin, gravity becomes increasingly irrelevant on large scales. Gravitational interactions still occur locally where mass remains, but they no longer shape the global evolution of the universe. The overall expansion dominates the dynamics, setting the pace at which distances increase and interactions weaken. At the smallest scales, quantum fields remain present. Even in regions devoid of particles, fields retain a ground state. These vacuum fields influence particle behavior and contribute to the energy density of space. However, without matter to interact with, their effects remain subtle and largely unobservable. Quantum fluctuations are often discussed in this context, but their role in the far future is uncertain. While fluctuations are a fundamental feature of quantum theory, their ability to generate lasting structure depends on amplification mechanisms that may no longer exist. Most models suggest that any such fluctuations would be short-lived and localized. Another unresolved aspect involves the ultimate behavior of space-time under extreme dilution. General relativity describes space-time well at large scales, but it does not incorporate quantum effects fully. A complete theory of quantum gravity does not yet exist. As a result, predictions about the far future rely on extending known theories beyond tested domains. Some approaches suggest that space-time itself could possess microscopic structure. If so, its behavior at very long times might differ subtly from classical expectations. These ideas remain speculative and currently lack observational support. They are mentioned to clarify the limits of certainty rather than to propose alternatives. Despite these uncertainties, there is broad agreement on intermediate conclusions. The universe becomes increasingly simple in terms of large-scale structure. Fewer components contribute significantly to its dynamics. Expansion dominates over interaction, and geometry dominates over matter. This simplification affects not only physical processes but also how quantities are defined. Concepts such as temperature, pressure, and density rely on ensembles of particles. As particle numbers decrease within any given region, these quantities lose precision. They remain definable mathematically but less meaningful physically. Radiation, while still present, continues to redshift. Its energy density drops faster than that of dark energy, making it dynamically negligible. Over time, even defining a background temperature becomes impractical, as wavelengths grow beyond any realistic scale of interaction. Neutrinos, which once played a role in early cosmic evolution, also become irrelevant dynamically. Their weak interactions and decreasing energy mean they pass through space without influencing its structure. They persist as a background component with little effect. As the universe becomes dominated by its vacuum properties, its evolution becomes increasingly predictable. There are fewer interacting components, fewer feedback mechanisms, and fewer sources of complexity. The trajectory smooths out, guided by simple parameters rather than intricate processes. This predictability does not imply complete certainty. Small uncertainties in fundamental constants or unknown physics could still alter outcomes over immense timescales. However, such effects would need to overcome the dominant influence of expansion and dilution, which appears robust across many models. In this phase, change continues but at a diminishing rate. Distances grow, energy densities fall, remaining processes slow further. The universe does not reach a sharp endpoint but continues evolving toward a state that differs only marginally from itself at later times. This gradualism is a defining feature of cosmological futures based on current evidence. There is no clear boundary between an active universe and an inactive one. Instead, there is a long transition during which activity becomes increasingly sparse. During this transition, the notion of scale becomes less intuitive. Length scales expand far beyond those associated with particles or remnants. Time scales stretch beyond familiar reference points. Comparison between epochs loses practical meaning because changes are so small. Yet, the underlying laws remain unchanged. Gravity, quantum mechanics, and thermodynamics still apply. They simply operate in regimes where their effects are minimal. The universe obeys the same rules, but those rules no longer generate dramatic outcomes. This highlights an important distinction between law and consequence. Physical laws do not guarantee complexity. They permit it under certain conditions. When those conditions fade, the laws remain, but their consequences diminish. The far future universe, as described by many models, is therefore not defined by new phenomena, but by the absence of conditions needed for familiar phenomena. Stars, chemistry, and structure require concentration and imbalance. Expansion gradually removes both. At this stage, cosmology shifts from describing processes to describing states. The universe becomes characterized by parameters rather than events. Expansion rate, vacuum energy density, and geometry define its condition more than interactions or transformations. This state is stable in the sense that deviations are unlikely to grow. Without mechanisms for amplification, disturbances fade rather than spread. The universe resists complexity not through force, but through lack of opportunity. Importantly, this resistance is not imposed externally. It emerges naturally from the same expansion that once allowed galaxies to form. The universe's future is a continuation of its past, shaped by the same dynamics applied over longer times. As a result, the far future does not require new assumptions to be understood in outline. It follows logically from trends already observed. The uncertainties lie in details, not direction. The universe continues, shaped primarily by its geometry and the properties of space itself. Matter and radiation become secondary, then negligible. What remains is a cosmos defined less by what happens within it, and more by the conditions it maintains. As the universe continues to thin and cool, attention shifts toward the fate of the smallest remaining physical structures. At late times, when stars and compact remnants are rare or absent, what remains is a dilute mixture of particles, radiation, and vacuum energy. The behavior of this mixture is governed less by interaction and more by persistence. Elementary particles that survive into this era move freely through expanding space. Their trajectories are largely unaffected by encounters with other particles, simply because such encounters are unlikely. The universe does not become empty in a strict sense, but it becomes sparse enough that interactions cease to shape large-scale behavior. The stability of matter over very long times remains an open question. Within the standard model of particle physics, protons appear stable, and no decay has yet been observed. However, some extensions of the standard model allow for proton decay on timescales far beyond current experimental reach. Whether such decay occurs remains uncertain. If proton decay is possible, it would gradually eliminate even the most persistent forms of matter. Atomic nuclei would disintegrate into lighter particles. Over enormous timescales, structures built from baryonic matter would dissolve, converting mass into radiation and low-energy particles. This process would further reduce the diversity of physical components in the universe. If protons are truly stable, matter could persist for extremely long times in isolated forms. Even then, change would continue slowly through other processes. Quantum tunneling, rare particle interactions, and gravitational effects would still operate, but with diminishing influence as expansion proceeds. Dark matter, another major component of the universe, also plays a role in late-time evolution. Its nature is not yet known, but it appears to interact weakly with ordinary matter and radiation. Depending on its properties, dark matter particles may be stable or may decay over long timescales. Current observations do not yet constrain this behavior fully. If dark matter decays, it would contribute additional low-energy particles and radiation to the universe. If it remains stable, it would persist as a diffuse background, influencing space-time geometry through its mass. In either case, its dynamical importance decreases relative to dark energy as expansion continues. As particle densities fall, defining physical quantities becomes increasingly difficult. Temperature, for example, relies on frequent particle interactions to be meaningful. In a universe where interactions are rare, temperature becomes a statistical abstraction rather than a measurable property. Similarly, pressure and density lose operational significance. They can be defined mathematically, but they no longer correspond to physical effects capable of driving motion or change. These quantities fade from relevance as the universe transitions toward a vacuum-dominated state. Radiation continues to exist, but with ever-decreasing energy. Photons stretch to wavelengths so long that they interact negligibly with matter. Over time, the distinction between different types of radiation becomes less important, as all contribute minimally to the universe's energy budget. Neutrinos, once abundant and influential in early cosmic history, also become dynamically irrelevant. Their weak interactions and low energy allow them to stream through space without effect. They remain as relics, but their presence does not alter cosmic evolution. At this stage, the universe's composition simplifies dramatically. Vacuum energy dominates, with small contributions from residual particles and radiation. The universe's behavior is largely determined by the properties of space itself, rather than by the contents within it. This dominance of vacuum energy leads to a further smoothing of space-time. Variations in curvature diminish as mass and energy densities fall. The universe approaches a state where geometry changes very slowly and uniformly with little deviation across large scales. In this environment, classical general relativity remains an effective description of large-scale behavior. However, questions about the ultimate fate of space-time require a theory that unifies gravity with quantum mechanics. Such a theory is not yet complete, introducing uncertainty into predictions about extremely late times. Some approaches to quantum gravity suggest that space-time may have a minimum scale or discrete structure. If so, its behavior at long times might deviate subtly from classical expectations. These deviations, if they exist, would be extremely difficult to detect or model reliably. Despite these uncertainties, there is little indication that new, large-scale structures would form spontaneously. Known mechanisms for structure formation rely on gravitational collapse and energy gradients, both of which become ineffective as expansion and dilution continue. The universe's evolution thus becomes increasingly monotonic. Changes occur, but they do not introduce novelty. Each state differs only slightly from the one before it. Over time, even these differences become negligible. In this regime, predicting the future becomes less about modeling complex systems and more about tracking smooth trends. Expansion rate, energy densities, and horizon properties define the evolution. The absence of competing processes simplifies the dynamics. This simplicity does not imply triviality. It reflects a system that has exhausted the conditions necessary for complexity. The universe is not constrained by rules that forbid change, but by the lack of resources required to sustain it. As expansion continues, causal regions become increasingly isolated. Within each region, the same general conditions apply. No region gains access to new energy or information from outside its horizon. The universe becomes locally self-contained. This isolation has implications for any remaining physical processes. Without external influence, systems evolve only under internal dynamics. As internal energy differences diminish, evolution slows further. Eventually, the universe reaches a stage where remaining changes are so subtle that distinguishing one era from another becomes impractical. The universe continues to age, but aging itself loses significance without markers or milestones. Throughout this long transition, the laws of physics do not break down. They continue to describe behavior accurately within their domains. What changes is the scale and impact of that behavior. The far future is therefore characterized not by dramatic events, but by the absence of them. It is defined by persistence rather than transformation, by stability rather than activity. This perspective aligns with the view that cosmic evolution is driven by simple principles applied over immense time. The complexity of earlier epochs arises from favorable conditions, not from special exceptions to those principles. As those conditions fade, the universe naturally returns to simplicity. Not abruptly and not completely, but gradually and consistently. The result is a cosmos shaped primarily by expansion and geometry, with matter and radiation playing only minor roles. The universe remains governed by the same rules that have always applied. Those rules no longer generate complexity, but they continue to maintain consistency. The far future unfolds quietly, guided by the same physical framework that shaped every earlier stage. As cosmic evolution proceeds under these simplified conditions, one remaining area of interest involves the long-term behavior of fundamental physical constants. In current physics, quantities such as the speed of light, the strength of gravity, and particle masses are treated as fixed. Observations place strong limits on how much they can vary, but they cannot rule out extremely slow changes over immense timescales. Some theoretical frameworks allow for the possibility that constants could drift slightly as the universe evolves. If such changes occur, they would likely be subtle and gradual. Even small variations, however, could influence late-time physics by altering decay rates, interaction strengths, or vacuum properties. At present, there is no observational evidence that such variation occurs, so this remains speculative. Another open question concerns the ultimate stability of the vacuum state associated with dark energy. While current data are consistent with a constant vacuum energy, this does not guarantee absolute stability. The vacuum could be metastable, meaning it appears stable but could transition to a lower energy configuration under rare conditions. This possibility arises in some quantum field theories, though it is highly model dependent. If a vacuum transition were possible, it would represent a fundamental change in the universe's structure. Particle properties, force strengths, and even space-time geometry could differ inside a new vacuum state. Such an event, if it occurred, would propagate at close to the speed of light and would not provide advance warning. Current estimates suggest that if such transitions are possible, they are extremely unlikely on timescales relevant to cosmic evolution as we understand it. Because of this uncertainty, most long-term models treat the vacuum as effectively stable. Under that assumption, the universe continues expanding smoothly, without abrupt changes in its underlying laws. This allows cosmologists to extrapolate trends forward using known physics while acknowledging that these extrapolations become less secure at extreme times. Another aspect of late-time evolution involves the fate of entropy itself. Entropy increases as energy spreads and accessible states are filled. In many cosmological descriptions, entropy approaches a very high value, but may not reach a strict maximum in a finite time. Instead, it asymptotically approaches a limit set by the properties of space-time and horizons. In an accelerating universe with horizons, entropy is often associated not only with matter and radiation, but also with the horizon itself. This suggests that total entropy within a causal region may be finite. If true, this would place a limit on the amount of information that can ever be contained or processed within that region. These ideas are still under active investigation and depend on how gravitational entropy is defined. As entropy increases, the capacity for organized processes decreases. This does not require entropy to reach an absolute maximum. It is sufficient that differences become too small to drive change. In practice, this means that even long before any theoretical limit is reached, the universe behaves as if it were in equilibrium. At such late times, even rare processes become stretched across enormous intervals. Events that once occurred frequently become separated by durations so long that they no longer influence overall evolution. The universe becomes dominated by waiting rather than happening, though waiting itself is only a metaphor for a lack of activity. From a modeling perspective, this simplifies cosmic dynamics. With few interacting components, equations become easier to solve in principle. However, the lack of empirical access makes these solutions largely conceptual. They describe states that cannot be observed, only inferred. Another unresolved issue involves the possibility of extremely rare gravitational events. In principle, remnants such as black holes or compact objects could interact through long-range forces over very long times. However, as expansion continues, the probability of such encounters decreases. Most models suggest that these events become negligible contributors to late-time behavior. Similarly, quantum mechanical processes such as tunneling remain allowed by theory but require specific conditions. In a highly diluted universe, the chances of tunneling events leading to macroscopic consequences are extremely low. Without amplification mechanisms, their effects remain local and transient. The absence of amplification is a key feature of late cosmic epochs. In earlier times, small fluctuations could grow through gravitational instability or phase transitions. In the far future, expansion suppresses growth. Fluctuations fade rather than accumulate. This suppression reinforces the trend toward uniformity. Differences do not propagate or combine. They dissipate into an environment that cannot sustain them. The universe becomes resilient to change, not through rigidity, but through lack of reinforcement. Another area of uncertainty concerns the ultimate fate of black hole entropy. If black holes evaporate through Hawking radiation as predicted, their entropy would be released back into the universe as low-energy radiation. How this entropy integrates with horizon entropy and vacuum entropy is still an open theoretical question. Some approaches suggest that total entropy continues to increase even as black holes vanish. Others propose that entropy may be redistributed rather than strictly increased. These debates highlight the incomplete nature of our understanding at the intersection of gravity and quantum theory. Despite these open questions, the overall picture remains consistent. Late-time cosmic evolution is dominated by smooth expansion, diminishing interaction, and increasing uniformity. The uncertainties lie in details that are unlikely to reverse these trends. As the universe becomes increasingly uniform, its description relies more heavily on symmetry. Homogeneity and isotropy become nearly exact on large scales. Deviations exist but are too small to influence dynamics. The universe approaches an idealized state that simplifies its mathematical treatment. This symmetry does not imply perfection. It reflects the averaging out of irregularities over time and distance. The same process that once amplified small differences now erases them. Symmetry emerges not from design, but from persistence. In this regime, cosmology becomes less about evolution and more about maintenance. The universe maintains its expansion rate, its vacuum energy density, and its geometric structure. There are no competing processes to disrupt this balance. The concept of a future becomes less intuitive under these conditions. Without milestones or transitions, the distinction between near and far future blurs. Each epoch resembles the next, differing only in scale rather than character. Nevertheless, time remains part of the physical description. Expansion continues as a function of time, and parameters evolve accordingly. What changes is not time itself, but its usefulness as a way to organize experience or events. This distinction is important for scientific clarity. Time does not cease, and physical law does not halt. Instead, the universe enters a regime where time labels states that are almost indistinguishable. Change continues, but its impact approaches zero. As the universe continues along this long, quiet trajectory, its future becomes defined less by what it does and more by what it allows. The physical laws that shaped earlier eras still apply, but they operate in regimes where their effects are minimal. Expansion continues, energy remains diluted, and the large-scale state changes only very slowly. In this setting, the universe does not approach a dramatic endpoint. Instead, it settles into a condition that is stable under small disturbances. Without strong gradients or dense structures, there are no mechanisms left to generate new complexity. Processes that once dominated cosmic evolution have either completed their course or become negligible. This outcome is not imposed by any single factor. It arises from the combined influence of expansion, thermodynamics, and finite resources. Each contributes incrementally, and over immense timescales, their effects accumulate. The result is a universe that becomes increasingly uniform, predictable, and simple in its large-scale behavior. Importantly, this picture depends on assumptions that remain open to refinement. Dark energy appears consistent with a constant value, but its nature is not fully understood. Fundamental constants appear stable, but extremely slow variation cannot be entirely ruled out. The vacuum seems long-lived, but absolute stability is not proven. These uncertainties are acknowledged within the framework, not ignored. Even with those uncertainties, the broad direction suggested by current evidence is clear. The universe continues expanding, matter and radiation become ever more dilute. Interactions grow rare, structure fades. No known, well-supported mechanism is expected to reverse these trends. As the universe ages further, the distinction between different components becomes less relevant. Whether energy exists as particles, radiation, or vacuum fluctuations matters little to the overall dynamics. All contribute weakly compared to the dominant influence of space-time expansion. At these late times, cosmology becomes a study of limits rather than events. It describes what remains possible rather than what is likely to happen. The universe does not run out of time or reach a final moment. It approaches a state where change continues, but without noticeable effect. This gradual settling is sometimes described as a form of thermal equilibrium on cosmic scales. The term should be understood carefully. It does not imply uniform temperature in a practical sense, nor does it require a final, perfectly static state. It reflects the absence of usable energy differences capable of driving further evolution. In such a universe, nothing compels further organization. Small fluctuations remain allowed by physics, but they are not amplified. Rare processes still occur, but they do not accumulate. Each change is isolated, absorbed into a background that remains essentially unchanged. The universe in this phase is not empty. Space still contains quantum fields, vacuum energy, and traces of particles. What has changed is the role these components play. They no longer interact in ways that reshape the cosmos. They persist without consequence. From a scientific perspective, this outcome is neither surprising nor exceptional. Many physical systems evolve toward equilibrium when left undisturbed. The universe, viewed as the largest physical system we know, follows the same tendency, guided by the same principles. What makes the universe distinct is the scale involved. The timescales are so large that ordinary intuition fails. Processes unfold slowly enough that, for all practical purposes, they appear frozen. Yet mathematically, evolution never truly stops. This distinction matters. Physics does not predict a universe that suddenly becomes inert. It predicts one that continues changing, but at a rate that approaches zero relative to any meaningful measure. The universe ages, but aging no longer carries visible markers. Because of this, the far future resists storytelling. There are no milestones, no transitions, no events to sequence. The universe becomes defined by state rather than history. Description replaces narrative. Within that description, space dominates. Geometry becomes the primary feature, shaped by expansion and dark energy. Matter and radiation recede into the background, no longer shaping the structure of space-time in a significant way. The simplicity of this outcome is not a loss of richness, but a reflection of completion. The universe has passed through phases where complexity could arise and persist. Those phases depended on conditions that no longer apply. Their conclusion follows naturally. Nothing in this picture diminishes the reality of earlier cosmic history. Stars, galaxies, chemistry, and life were not temporary accidents. They were expected outcomes of the universe's initial conditions combined with physical law. Their eventual fading does not negate their significance. The universe does not carry memory in the way living systems do. It does not preserve a record of what once existed beyond the laws that allowed it to exist. When structures dissolve, the traces they leave behind disperse. Over enough time, even those traces become indistinguishable from the background. This does not represent erasure in an active sense. It is simply the consequence of dispersion. Information that is not maintained by structure spreads until it can no longer be recovered. This process is gradual and unremarkable, consistent with the rest of cosmic evolution. As cosmology looks ahead, it does so with caution. Predictions are framed by models that work well within observable ranges and are extended carefully beyond them. Confidence decreases with distance in time, but the overall direction remains supported by multiple lines of evidence. What emerges is a universe that becomes quieter, simpler, and more uniform. Not abruptly, not completely, but steadily as expansion continues and interactions fade. The universe remains governed by the same principles that have always applied. In this final view, the universe does not end. It continues, extended and consistent, without urgency and without climax. Its future is not a destination, but a condition approached ever more closely. There is no requirement for a final event, no need for resolution. The universe does not conclude a story, it completes a process, and in that completion, nothing more is demanded of it. The cosmos remains vast and even, changing only in the most subtle ways, following its laws quietly and patiently, as it has always done. Good night.